All right. Well, hello everybody and welcome to today's session. So we are continuing our MLOps journey from last week. So last week we started a use case, which is medical image processing. And I know most of my viewers here are in that domain. So we talked about how to create a data pipeline for 3D medical image stack. So whenever you have not just one image, but a few image stacks, how would you go about ensuring that you have a data pipeline? And today we will be talking about how to create a ML model, around it. So one of my most popular videos so far has been on Unet. So that's the reason why I decided to extend that particular work. So I wanted to show you that today I will be working off of an OCT image stack. And the OCT image stack, it actually looks like this. So let me make the images bigger. So these are what the OCT images look like. And if you see, all of these images are actually acquired for the same patient. So these are 3D, the third dimension of the retinal image for human eyes, and they are telling you what is the thickness of every single retinal layer is. And ideally, if you have regions of interest such as this, so these are called the retinal cysts, which you need to segment for. But if you just segment per image, then that's not enough. You typically require multiple images in your cysts in multiple images to be segmented so that you can reconstruct the volume of the cyst that has happened. So these cystic regions, they are filled with some fluid. So ideally you need to figure out what is the volume of amount of fluid in these particular cysts so that then your prognosis or your treatment process can work accordingly. Now, working with single shot images, mostly such as if you're doing something like a skin lesion, or if you're looking at the retinal images only, then those are just single images per patient. So those are relatively a different mechanism works for them. But especially when you start having video frames or videos or 3D image stacks. So if things are varying in time or space, in this case it is the space, the region is changing. The ML models have to be treated a little differently. So that's the reason why today we are assuming that our starting points are volumetric scans such as this, right? And in these cases, the ground truth, again, as you see, it is the cystic regions that have been marked off in each and every one of them. And what you really want to do is generate predictions that look like this, where you have the cystic regions have been actually marked off as accurate as possible. Like some places you see that they are not very accurate, and that is mostly because the cystic region is not as bright as the remaining images. So if you train with very minimal number of images, you will get minimal amount of performance. So that's the reason why we are starting with this is the problem statement. We want to look at the images that are CT images, and we want to generate semantic segmentation. But today, and I know in most of my videos I've talked about this model which is called Unet, but today I will be talking about a different model which is called Unet Plus. And this came out a few years back in 2018. It's called a nested Unet architecture, and here or the number of intermediate steps is actually more. So the computation complexity, if you may say, is a little higher, but the accuracy is also higher. And you can literally see at every single stage how the performance is shifting. So that's the reason why I chose this model rather than the standard Unet. And I am going to be going over every single step as it progresses. So this is the GitHub. So I will be linking the paper, and I took the main model into the description box below so that you can try it out yourself as well. I wanted to first talk about the Unet Plus model so that we are all on the same page while we do our coding. So a Unet Plus, ideally what would have happened is if you were talking about just a unit layer, then again, it would have started from this particular stage where you do your convolutions, and then you do your batch normalization. And at the end of the day, you do a max pooling and you pass it to the next level. So whenever it's going down like this, that means it is downsampling, and you do downsampling by the use of max pooling, right? Now, once you have reached this particular layer, then what happens? Then you start upsampling the images. So you upsample and again take it back to the same size as the original image size. But what you also do is all the intermediate upsampled image, you actually put them together. So the same size downsampled image and the same sized upsampled images, they are actually combined together to concatenate. And it has shown that this concatenation helps the CNN to better distinguish background from foreground images. So that's the reason why these are just concatenations or skip connections, essentially, where you are combining these intermediate layers. So ideally, in a Unet, these intermediate yellow blocks that you see, they would not have existed. You would just have had simple skip connections going from this X10 to X13 directly, right? So they would be just a single connection. However, in Unet, what it does, the number of intermediate images are actually more. So what it does is, instead of just taking it to one skip connection, corresponding to this skip connection, there is also an upsampling. And then there is also a merging of this upsampled version with the previous downsampled version. So you see, there are a lot more intermediate steps that you are now detecting. And the idea, the concept behind it is exactly the same as that of ResNet. It says if you have, if you take the previous layers and you upgrade that along or concatenate that along with a version or intermediate layer, then there is more information that comes from the previous layer to this one. So if there was any vanishing gradient problem, then that ideally would be taken care of. So ResNets take care of the vanishing gradient problem. Same thing is done here. You are now just adding more detail into the intermediate skip connections, and because the skip connections are way more detailed right now, you are ideally supposed to catch if there are any boundary conditions or any more neighborhood regions that were lacking beforehand. Now they get caught in a better way. But the other advantage that Unet Plus also poses is now you can actually see your output at all these three layers or at all these three different levels. So step number 3.1, step number 2.2, step number 1.3, and step number 0.4. You can literally look into the outcomes of each and every one of these layers, and you can see how the performance is improving as you go from the very rudimentary first level sampling to the second level sampling, to the third level sampling, and the fourth level sampling. And I'll show you how that works, right? So in some cases, it might even happen, maybe the third level sampling is good enough, in which case you should have ideally, reduced the depth or the Unet depth and made it to three levels only. But yeah, that's for later. But what I wanted to show you is how we actually go through all of these different depths and actually see how the performance is changing. So that's just the background. This is what we are using. And now we are going to get into our code. So I'm just going to make it larger so that you can see this well. It needs to be here. Okay, all right. So what I am first going to be doing is I'm just mounting my drive, my Colab, so that we can start getting into we can start accessing the images, right? Because the images, they're all mounted in my Google Drive. So first, I'm just going to be, checking all of my files are here. And I'm just, importing all of the libraries that's required. One thing that I did want to mention is in this particular GitHub, the only file that is there is called this file model.py. So all you need to do is take this file model.py. Like I have had to modify this significantly, so I will make my code available in some time. But in the meanwhile, you can definitely start working off of this model. What I wanted to show you here is they have defined this class, or this is actually a function. So they have defined a function called Unet, and then they have another function called WUnit, which is called the weighted unit, which is used for comparison. And then the third function is called the nest. Now the nest is actually the Unet Plus. And here you see we will be applying deep supervision level. And in the deep supervision level, you literally can see these different outputs. Like I mentioned, it is output corresponding to the depth level 1, output corresponding to depth level 2, depth level 3, and depth level 4. So you will be able to see each and every one of them. And I'll show you how the results vary as well. So that is the model file that I am going to be importing. That's all I wanted to mention here. And the image size that I'm resizing it to is 256 by 256. The classes that I have, again, it's background versus foreground. So that's the reason why I'm keeping it at 2. So this is the, these are the parameters that I'm passing to it. It's 256 by 256 images. And I am taking it through deep supervision so that I can see exactly what is happening at the different depths. All right. So, and again, you can definitely try out with just the Unet. And again, once if we finish quickly, I can show you how the parameters change as well. So if we just do a model.summary, you will see that for Unet++, the number of total parameters is somewhere around 9,000 parameters. 9 million parameters is what you need to tune for this particular instance. So that is not small, but what happens is for medical images, the pixels are so similar, you don't really need 9 million samples to train it. You need way less than that. So that's the reason why for medical images, this is not going to overfit. It's still going to work. All right, so now let's go to the basic functions. Again, these functions remain same. I will also be linking my other Unet video in the description box below. So if you want to know about the exact what are these functions, what they are doing, everything will be explained in the previous videos. So it's the same thing. It is just in order to train to augment the data. But what I wanted to also show you is evaluation. So in the last few videos, I've not been showing evaluation and metrics. In this case, because it's semantic segmentation, evaluation is again, regions of interest. So precision, recall, IOU, intersection over union, and accuracy and F1 score. So accuracy, I'm calling it pixel level accuracy, and F1 score. So everything put together. That's the parameters that I'm going to be evaluating against. So first of all, let's just pass all of the folders. And here, this is just making sure that if I want to augment, then I have the way to do that. So I'm initially augmenting just using 3 images, right? So 3 sample images are going to be used together in order to generate augmented images. And this is where I'm actually changing the kind of model compiler. And if you see, I've actually experimented with a few options. One option is the most commonly known as just binary cross entropy and accuracy, but it is very, very well documented that binary cross entropy loss for semantic segmentation is not a very good option. Typically, you need something which is a little more conservative for intersection over union sort of, loss functions. So dice coefficient loss or BCE dice loss, these are actually better metrics. And also metrics wise, dice coefficient is actually a better one. So I'll keep it at the dice coefficient loss. And again, the loss function is exactly the same as the Unet example that I've worked on. So let me run this. And of course, it would have been better if I run up till 50 epochs, but just for today, I'll just run it for 10 epochs so that we should at least get to know what is happening in the background. And while this will be running, I'll be showing you or how you can modify it for your own applications. What are the some of the changes that you will probably need to make. So the first things first is if you are applying, if you're using it on Colab, make sure always that your session is running with GPU. If not, you should terminate it and always start with GPU. And here you see, because we are working with the deep supervision, you will see that there are multiple loss functions that get reported. So there is the output loss. Then there is output loss from level 2, then level 3, and then level 4. So all of these losses get reported and all of these outputs are also reported. So essentially, you are not just getting one layer of output, right? You have an input, you have an input image 256 by 256. You're not just getting 1 256 by 256 images, but you're getting 4. And these 4 are corresponding to 4 of the different depths at which these images are getting computed, right? So let me show you what that really means. So let's go back to this is the, the main paper here. Let me make it a little larger. So in case if you have to change it for your data set, the first off, you need to make sure that the size of the image that you want to pass. Typically, I've seen 256 by 256 to 512 by 512 is something that a Colab GPU can handle. If you want something larger than that, then the best ideas would be to break down the images into, so subsample the images essentially, and then reconstruct it back. So, break them down into smaller patches, whatever patch size you intend, and then put them back together. Patching is, I have seen patching is not always a good solution when they are one-dimensional images. For three-dimensional images like RGB images, there is enough structural data for the regions to still find similarity and the matching to happen well. But if you're using like CT images, and if these are poor quality CT images or poor quality like OCT images, they're not good quality at all. In those cases, what I've seen is styling really doesn't help, because the algorithm gets confused. That there's not enough information in order to put the patches back together. So that's generally just a recommendation. So you'll have to change the size of the image in the beginning. And also in nested unit, the good thing is you really don't have to experiment anymore if you have to take a depth of 3 or a depth of 2 or a depth of 5. Right? Why? Because you will have access to all the intermediate layers anyway. Right? So that's the reason why you don't even have to say, okay, I have to, one of the hyperparameters is the depth anymore, because now you will automatically have depth 1, depth 2, depth 3, and depth 4. And if you see depth 3 is better than depth 4, then you know your Unet plus the ideal depth is at 3. Right? So these are some of the advantages that Unet plus has over a normal Unet model. Now, I think this is finished running, and this is, let me plot the loss plots. And this loss plot is now going to tell you, so these are all the different epochs. Of course, I ran it just for 10 epochs, but now you see this is the different depths. So this is depth, so output depth 1, output depth 2, depth 3, and depth 4. So here you can definitely see that depth 4 was better. And that's where you're getting the best loss functions. Again, hyperparameterization, the tuning will be mostly for your your learning rate and what kind of optimizer you're using here. Now let's generate the results, and this is how I'm predicting it. I'm not saving it yet because I already have previous results saved from the previous outcome. What I wanted to show you more is the evaluation and some of the results at the different levels. So as you see, the shape of the results, like I mentioned, so there were 25 images, and for every image now it is returning 4 image planes because it is the output at depth 1, 2, 3, and 4. Now let's try to visualize each and every one of them. So here I am I'm printing out the result at the final, so depth 4, and this is image 5, right? And this is just the 0th plane. So at the final depth, sorry, this would probably be an odd image. Let me try out. Okay, I think this has not converged. That's the reason why. Yeah, this image this is not converged. So what I'll really have to do is I'll have to allow it for more epochs. So this is a good learning experience, right? So that means just doing 10 epochs, it doesn't really convert. So you'll have to run it for at least 40. So let me initialize this back. And this is a good debugging exercise for us anyways, right? So I'll have to first reinitialize this. Rerunning something, you should always start from reinitialization. Otherwise, it will assume that your point from which you're starting is just the previous location, and it will restart from there, which is not going to be accurate. All right, so this is going to keep going, and once you have seen the loss functions, we will be able to then look at what the outcomes are. I did want to talk about the evaluation function first. So the evaluation function, as you see the eval result, and I will show you once the results are out, you will be able to see, and if you compute them, that this is the results at level 0, which is mine. Level 0 means depth level 1. This is depth level 2, depth level 3, and depth level 4, right? So at every single point, now I'm computing the precision, the recall, the IOU, and the F1 score. And as you can see, definitely depth 1 is not good enough, right? So your F1 score is pretty low. But then as you go from depth 1 to depth 2, you see the precision increases quite a lot, pretty significantly actually. And then in this case, the depth 3 was actually the best one, because you see it's 0.83. So it's actually 0.84. So which is actually higher than what you would get at one more level depth, right? So ideally what this whole set of results is showing you is that in this case, for this particular instance of Unet, a depth of 3 was good enough. So while you go to depth 4, you are adding 4 extra neurons in order to go from the skip connection from the from the image here to the final outcome. And these are at this point just going on adding nodes, right? So this was a valuable observation that just increasing depths is actually not helpful. But because Unet Plus now you can literally threshold and figure out what are the outcomes at each and every level. If F1 was your metric of choice, then you should have stopped at this particular level. However, if your metric of choice would have been precision, then you couldn't have definitely gone for the fourth, the final level. So that is what your Unet Plus is telling you. Let's see. Okay, 40 are done. So let me plot all of the loss functions, and let's see if I generate the results. And this is done. Result shape is done. Finally, okay. So this is the at level 3. So let me take the image 5. I saw that that there's a lot of definition here. So this is the output at the 5th level. Sorry, at the 4th level for image number 5. Now let me show you what the output happens. Let's start from the beginning, right? At output level at 0, so depth level just 1. What is the output? So you see here the cyst is not well segmented, so that's why this is not the ideal result, right? Now you go to depth level 1. At depth level 1, you see a significant improvement, and this is what we can see qualitatively as well, right? Now if we go to level 2, again, very difficult to figure out the differences between these two. The most significant differences are actually around the edges, the bounding boxes, the edges. And now if I go to the final level, then this becomes my output. So the edges become a little more defined. So if we go to image number 6, you will be able to see the same thing. So let me go to the first level for image number 6. Again, you see it's a very broken down cyst, not very well defined. Now, if I go to the second level, the definitions are way better, right? You see a significant improvement over the previous one. And then if I go to the next level, you see that one false positive, now that has gone away. And finally, number 3, you see the definitions are way better, right? Around the edges. So this is how you will be able to access the different levels of the regions of interest using Unet Plus. And again, the regions of interest, the evaluation function is exactly the same as that I had in my unit in the other unit examples. It's just in this case, I am passing it one of the planes at a time, so that I can literally evaluate for what the performance is at different depth values. So that was the exercise that we saw today. Now I'm going to stop sharing and look at some of the questions so that I can answer. All right. So let me see. So Venkatesan, you ask transfer learning models like VGG, ResNet, EfficientNet, Unet encoder, decoder blocks, which gives better performance based on my experience. So for this, and there's been a lot of literature actually out there. ResNets have, even for Unet, I think there is a ResUnet that has, yes, there's been a ResUnet that was also proposed some time back. In my experience, I have seen Unet has actually always given better results in terms of generalizability and computational complexity. I actually came across a very recent paper that was looking at COVID-19 segmentation, semantic segmentation of lung scans. So in Kaggle, there is a lot of open data set. And there they were literally comparing the performances of all the models that you're talking about, ResNet, VGG, and EfficientNet. Now, EfficientNet, of course, it's very efficient in terms of the number of parameters, but it always showed that Unet's generalizability. So if you have already a pre-trained model, let's say on something like an OCT stack, because you know what should the earlier filters should look like. But for you to take that and modify that quickly to a COVID-19 lung scan, it's super easy, and the parameters are low and the generalizability is high. And that's one reason why I've seen, Unet has been so popular. It got on, more popular than most of the other models. Like they were fully convolutional neural networks, but Unet, especially for medical imaging, it has been found to be extremely powerful and generalizable. Inputs or video related to the biomedical books preferred, challenges that will help beginners. Well, frankly, for my own knowledge purposes, I follow research papers way more than I follow books. Because what I believe is books, again, they are a static, they're a snapshot of whatever has happened so far. But then the community is changing so rapidly, and models are coming in so at such a pace, it's really hard for any textbook to keep up with it. So if you ask what I do, I typically just go to computer vision and medical imaging conferences, and I check out papers there. If it is semantic segmentation, like for instance, right now I'm really interested into lung scan segmentations. So that's the reason why I'm looking into the Kaggle contest and seeing what has scaled so far the most, and that's where I'm finding Unet typically is always a better solution. So I could even, if you want, even link that paper in the description box below that was comparing all of the different models, like the efficient net, VGG, ResNet, and each and every one of them, and comparing there. Hello, Shubham. If you have a question, please do type it in the chat. I'll be hanging around for another few minutes. At the end of post processing, will you include region property measures like area, centroid, perimeter? This is an interesting question. It completely depends on the use case that what you're doing. So if we go back to the example that I was showing you, in that case, I actually didn't have any post processing. So the results that you showed that I showed you, they're actually just exactly from what it has been computed. But in some cases, you may. But the example that I showed you today did not need any thresholding. In some cases, for instance, whenever I was doing my diabetic retinopathy detection, in those cases, or even with the lung segmentation, I think there is this two regions of interest. One is called broken glass, where you're literally finding the regions corresponding to where the person has in the chest, in the lung scans, where wherever you see congestion. So those are called broken glass regions. But whenever you have things like broken glass regions, it's really hard to figure out area, right? Because it's not very, very, very uniform. So in those cases, per pixel, region information is more important rather than, some of the other properties like such as area, centroid, perimeter. Area, centroid, perimeter, I've seen that these regions become more useful whenever you're talking about things like cyst, or if it's a tumor, whenever you are trying to figure out features corresponding to prognostics, right? So if there are this many, if the cyst looks like a particular 3D generation, then this would be the prognosis. Studies, yes, it would be super useful to compute, regions like area, centroid, and your CV, CV2, OpenCV allows for you to do all of them. So in order to take all of the pixels to find the best fit, circle around it to find a major axis, minor axis, solidity, solidity is the convex area divided by the area, or I believe it's the opposite, area divided by convex area. So you can find all of those features, and yes, they become super important if you're doing prognostics, not really for diagnostic medicine. Shubham, your question is, you're using Label Me for image annotations. That's great. Please suggest another open source tool. Well, typically I've seen, so Labelbox is I think another one of the solutions that some of my subscribers have watched. I have used GIMP a lot. And GIMP is again another open source tool which requires absolutely no coding background. So whenever I work with doctors, they can't use Label Me because it's Python. So that's the reason why I always prefer it with people who have absolutely no coding background. So it's called GIMP, and the GIMP tool is I'm even typing it here. So the GIMP tool, it enables that. It looks just like Adobe Photoshop. The old days when there was Adobe Photoshop, you could literally have a layer and draw, and when you can literally save your files as a JPEG or a GIMP format. And I even have a video on it, so please do check out a video on GIMP. I think that would be helpful as well. All right, so that was our session today. Thank you so much, guys, for joining. I am actually working on this Unet Plus that you saw. I'm actually working on a research paper right now that converts it, that takes it from OCT to something like the lung scan images that I was talking about. I have a deadline coming up next week, so once that's done, I'd be glad to share the results from that with you guys as well. All right. Thanks again for joining. And